Hello everyone, my name is Srinivasan, and today I'll be talking about some recent work on the development of colloidal quantum dot LEDs and our recent findings on probing the electric field inhomogeneity inside of colloidal quantum dot LEDs towards improving them towards microdisplay applications. Just as a quick overview, I know we've heard a lot of talk about quantum dots, but quantum dots are these amazing, scalable, bright, efficient emitters, and we hope they can be used for the next generation of display technologies. And I thought it was very interesting to look at kind of the role of television displays and display technologies in the United States energy consumption. So in the year 2020, there was around 3,000 terawatt hours of energy consumption in the United States, and around 2% of that was consumed by television displays. And so if we can find any way of making these displays more efficient, such as by using these colloidal quantum dots directly as electroluminescent centers, then we can make a pretty significant impact on energy consumption. And these quantum dot LEDs can cover a wide color gamut because they have very narrow emission, as we've seen many of the speakers today discuss. However, I kind of want to talk about the current state of the art for processing quantum dot LEDs, which is stochastic processing. So if we take a second to compare quantum dot LEDs to their kind of rival technology, organic light emitting diodes. Here we have an example organic emitter. It's around 1 nanometer in size. And when you make an organic LED, you're targeting active layer thicknesses on the order of 10 to 50 nanometers. And that single molecule that you're depositing onto your OLED stack won't change the thickness of your active layer very much. You have very smooth interfaces and very controlled thicknesses of your active layer. However, we compare that to quantum dots, where each quantum dot is on the order of 10 nanometers. And in our devices, we are targeting active layers on the order of 20 to 30 nanometers, which means that in a single device with stochastic processing, such as spin coating, inkjet printing, etc., we might have different monolayer thicknesses happening across the device, where we're going from a layer of 2 quantum dots to a layer of 3 quantum dots or 4. And every additional quantum dot is a significant change in your active layer thickness. And what we've seen is a significant change in the electric field homogeneity across the device. And the way we're probing that in our colloidal quantum dot LEDs is by using spatially resolved confocal photoluminescence and electroluminescence mapping. So what we can do is we can take our LED and we can place it on a piezo stage, which has kind of nanometer positioning accuracy, and we can basically generate these spatial maps of the photoluminescent intensity, as well as the electroluminescence intensity of the same region of the device by applying a DC voltage source to our LED while it's on this piezo stage. So this is the same region of the device, and we can generate these photoluminescence maps where we're exciting it with a laser source, and we can generate electroluminescence maps where we are applying a voltage to our device. And what we see in these images is that we have these EL dark spots, which are strongly spatially correlated with the position of photoluminescent hotspots in our device. And these EL dark spots and PL hotspots occupy around 5% of the active device area. Now, this doesn't necessarily tell us what exactly is happening inside the device. However, we can, because we have the ability to apply a voltage source to our LED, we can further probe what exactly is the mechanism for these EL dark spots and these PL hotspots. So what we can do is we can apply a reverse bias. So we can apply a negative voltage to our LED and then try to photoexcite this quantum dot active layer and understand the mechanism for the quenching of the photo-generated excitons under a strong reverse bias. So if you look at the relative photoluminescence intensity, as we apply a strong reverse bias, we can see a decrease in the total intensity as these photo-generated excitons are extracted out of the device. We're basically running our LED as if it's a photodetector or a solar cell. And we can perform the same kind of mapping, the same kind of photoluminescence mapping under these strong reverse bias conditions for, again, the same area of the device. These white arrows are just kind of indicating kind of similar features between these two images. And what we see is we see an overall decrease in the photoluminescence intensity, but we still see these PL hotspots that are retained under the strong reverse bias. So clearly there is some kind of morphological difference between these bright regions and these dark regions. Across a range of applied voltages ranging from just before turn on, this is 1.5 volts, all the way to -5 volts, we can see that the PL hotspots are always brighter than this uniform background, which indicates, again, some strong morphological difference between these hotspots and the background. Furthermore, because we are taking images of the exact same region of the device, what we can generate are these PL quenching efficiency maps, which show the spatial inhomogeneity in the quenching efficiency of these different regions of the device. So what we can do is we can perform pixel by pixel intensity divisions and generate these new maps, which are tracking spatially across the device PL quenching efficiency. So a very low PL quenching efficiency value means that under a strong reverse bias, a lot of your brightness is retained under photoexcitation. And a high PL quenching efficiency value indicates that under a strong reverse bias, you're able to extract those photo-generated excitons. And what again we see across all of these images is that these regions that we note are PL hotspots, and the regions that we note are EL dark spots are also regions that have low PL quenching efficiency. And all these three images together can be explained if we are tracing the local variation in the electric field across the QD-LED. So under forward bias, these regions are not strongly coupled to our electric field, and so they have a lower electroluminescence brightness. Under a strong reverse bias, those same regions are shielded from our electric field, and photo-generated excitons are not being quenched by our reverse bias. We can further probe this variation in the electric field across the device by performing these spectral diffusion measurements inside of our thin film to reveal information about energy transfer between these quantum dots. So as a quick background on spectral diffusion, if we have a dilute solution of quantum dots, where each quantum dot is isolated from all of its neighbors, then when we photo-excite this dilute solution and we track its emission energy, so this is energy on the x-axis here, and this is time after photoexcitation on the y-axis, we can see that the dilute solution of quantum dots, where each quantum dot is isolated from all of its neighbors, just emits one central color, and there's no shift in that color of the emission. These are red indium phosphide quantum dots. However, when we take those same quantum dots and we make a thin film of these quantum dots, now we can have energy transfer between each of these quantum dot centers, and we see a distinct red shift in the emission energy as a function of time. And we can explain this by saying that some of these excitons have higher energy states, and those higher energy excitons can transfer their energy to lower energy exciton states, and at long time we just see emission out of these low energy states, and we see this distinct red shift. Now this is what we expected to see inside of the thin film inside of a QD-LED. However, we saw an anomalous non-monotonic spectral diffusion signature. So if in a thin film we have a single red shift as a function of time, here in our LEDs we have an initial red shift followed by a blue shift at this kind of long time component. And to understand what is happening inside of our device, we can basically model the spectral diffusion signature with two populations of quantum dots that have different field interactions with the electric field and different mobilities. So what we found is that there are two species of excitons. There are more mobile excitons and less mobile excitons, which is what we have dubbed them. And these more mobile excitons are characterized by very fast spectral diffusion. So these are the species in red here. These are transferring their energy very rapidly to their neighbors, and they're interacting very strongly with the electric field, and so they have a very low exciton lifetime. The less mobile excitons are not spectrally diffusing very strongly, and because they're not interacting with the electric field, they have a very long exciton lifetime. And what we see is initially, our population is dominated by these more mobile excitons, and so our signal has this initial fast redshift, and at long time, after all of these mobile excitons have been quenched, the signal is now dominated by the emission from the less mobile excitons, and we see this return back up towards the less mobile exciton decay curve at long time. And so we can fit very nicely both the photoluminescence intensity as a function of time, as well as the photoluminescence energy as a function of time by invoking these two populations. And from these fits, we find that the immobile exciton population is around 3%, which fits very closely with our spatially mapped images, where we find that around 5% of the active area of the device is less reactive to the electric field. And this model kind of relies on these less mobile excitons being isolated or shielded from the electric field by these thicker regions of the quantum dot active layer that is generated during spin coating or inkjet printing or other stochastic processing techniques. So again, to kind of quickly summarize, we are able to directly visualize electric field inhomogeneity inside colloidal quantum dot LEDs using this microphotoluminescence and electroluminescence mapping technique. So under a reverse bias, excitons that are generated inside the thicker regions of the device are shielded by the thicker regions of the quantum dots that are on top of this, this thicker region. And so we see that these regions have lower PL quenching efficiency. Similarly, in the kind of reverse case, these thicker regions of the device have a larger capacitance, and so we see less electroluminescence in those exact same regions. And so between both of these images, we have a direct visualization of the local electric field on this kind of micron scale. Now, we believe that these variations in the local electric field may be driving some of the degradation, device degradation that is being reported with colloidal quantum dot light emitting diodes. Specifically, the inhomogeneity in this electric field might be driving degradation in the regions of the device that are actually experiencing electric field, and we have parts of our device that are not contributing to our brightness and are also not contributing to device degradation. Furthermore, we believe that the development of micro quantum dot LEDs, where we're using colloidal quantum dot LEDs as the luminescence center in micro LED displays, which might be on the order of 20 to 100 microns, might be limited with stochastic processing. If we are seeing brightness variations on the order of 5%, then stochastic processing may not be the best path forward towards developing colloidal quantum dot LEDs for micro display applications. So I'd like to acknowledge both the Buendia lab as well as the One lab here, which is what I'm representing in today's talk. This work was sponsored both by the Kiar project as well as the Samsung project. So thank you so much for listening.
Yeah, thank you. So you're attributing these variations to basically distribution of energetics, but I'm wondering if there's any sort of physical inhomogeneity. I'm thinking of like percolation phenomena. So is the charge or exciton transport, is it broad enough that you don't have to actually worry about the local structure, or could the structure actually be driving some of these behaviors?
Yeah, so thank you so much. Great question. So we do believe that it is the local structure that is driving this inhomogeneity. So if I here, so yeah, these are cross-sectional TM images of the device in question, where we can see that there are differences in the quantum dot layer height, and we believe it's these layer height differences is what we are kind of directly measuring in these electroluminescence maps and photoluminescence maps, so that these regions here are regions where we have thicker regions of the device, and it's that physical structure that is impeding your charge injection and transport through the device.
Percolation phenomena show a threshold like they're pretty far away from that, or is there any indication that percolation is actually?
I'm not totally familiar with the phenomenon you're discussing there, but we don't believe. Well, yeah, I guess we can chat afterwards, but I'm not totally familiar.
Yeah, thank you for a great talk. So this is very important phenomenon. Then what is the solution to make the even film?
Yeah, so kind of two strategies that we're thinking about is one, either kind of directed deposition or like a self-assembly of these quantum dots into even monolayer thicknesses, or if we can improve the matrix that's around the quantum dots. So right now these quantum dots are supported by organic ligands. If we can have a matrix that has a high mobility, then maybe it won't matter so much that there are these differences in the electric field if we can make the quantum dot layer kind of less insulating or more mobile, so that excitons can, or charges can freely diffuse into these thicker regions of the device and allow them to generate excitons. So there's kind of two strategies there.